So I hope I'll do good for them. Let's see. How's this? Yeah, okay. So this is what I'll do. I'll talk for a few minutes on the traffic signal control problem. Then I'll switch and describe our technical approach. I'll give you some results of the experimental study that is described in the paper. And actually, since the paper's been submitted, we've been engaged in a pilot implementation of the strategy. And so I'll talk for a few minutes at the end about the results that we're getting there, and then give some concluding remarks. So traffic is a great problem to work on. Everybody can relate. I'm sure you've all experienced this kind of situation. You know, and if you look at the statistics, there's a tremendous opportunity for improvement, both in the sort of the personal well-being of travelers and also the pollution and emissions to the environment. Traffic signals, better traffic signal control really can make a difference. You know, it's generally recognized, at least in urban areas, which has been our particular focus, that traffic signal control improvements are really the biggest payoff for reducing congestion. You know, it's you can get 10 to 20% reduction in travel times, or you're expected to get that, by just doing some amount of coordination over basic non-interconnected signal systems. And you know, an interesting statistic is in urban areas, vehicles spend approximately 40% of their time idling. So you can imagine the derivative effects if you can improve flows in reducing pollution and various carbon emissions. So what is the problem or the traffic signal? Oops. And although they're not really in wide use now, the what are called adaptive traffic signal systems are really believed to hold the most promise for improvement. They've had the most success to date, more in arterial kinds of situations, but systems that actually respond to the sense traffic and adjust the timing plans based on the travel. So, what is a traffic signal plan? If you look at it, if you analyze the flows moving through a particular intersection, you can really partition them into what are called movement phases. And these are really traffic flows that can proceed simultaneously in a safe manner. So you can see that here, flow 2 and 6 going in opposite directions obviously will make up one phase because the vehicles can move there. And then a signal timing plan is simply an ordered sequence of phases. So you'll notice here. You'll notice here that in the diagram I've given here that the sequence of phases repeats itself, and that's typical. It's not always that way, but that's typical. And we'll actually make that assumption in the paper, and it just corresponds to the green lights just sort of moving around in a cycle. The entire trip around the lights is called a cycle through the phases, and then you repeat again. So conventional signal systems use fixed pre-programmed timing plans. They may be developed given some kind of offline analysis of the loads that are expected and so on, but they're programmed in advance, potentially timed by period of day, and then given to run in open loop. Adaptive signal systems, on the other hand, sense current traffic flows and dynamically adjust the timing plans in real time. That's the class of problems that's the class of system that we're interested in and we'll be talking about today. So it's still quite a challenge to accomplish this kind of real-time adaptive control. Many of the adaptive systems today do in fact adjust to changing traffic flows, but do it on time scales that you would not really consider real time. Maybe every 5-10 minutes, you know, so it's more of really of tracking traffic flows and moving on from there. Well, what are some of the challenges to doing actually real time? Well, from a planning perspective, the complexity is great. In the state space, given a particular prediction horizon, the state space is exponential, the action space is exponential, even for a single intersection. As you put that together into a road network, the problem just becomes more and more complex. So the combinatorics are high. There's also, we're learning this firsthand, there's a lot of uncertainty associated with the sensing devices, and coping with that is very, sensors aren't perfect, far from it in fact. And then finally at the network level, there are non-local impacts between intersections. So again, that's a complicating factor. One nice property here is that there is a network problem structure. The relatively small numbers of connections between a complex of intersections. So that can be exploited. So what is our technical approach? We basically start from a very bottom-up view of decentralized intersection control. So at the ground level, we make an assumption that there is no interactions from intersections, and the idea here is to build a robust substrate that will always keep the traffic moving with somewhat the right direction. So the idea here is to construct schedules to optimize real-time traffic flow through each intersection. This is done independently and asynchronously. Then on top of that, we layer what we refer to as an optimistic non-local coordination mechanism. And the idea here, in a nutshell, we assume that intersections will execute their schedules as planned, and if that's the case, you know, we will have perfect coordination. So essentially this translates to providing schedules to downstream neighbors, and this just increases their visibility in an extended planning horizon. And then finally, on top of that, we add mechanisms for coping with particular situations of miscoordination. And in this paper, we look at preventing a nervousness effect due to a limitation due to mismatch between planned and actual execution, and preventing spillback, the phenomenon where cars are backing up into the intersection because there's not enough physical space. So here's the concept of operation. Let's see if I can. This is taken from our pilot implementation here, but the idea is current traffic conditions are extracted from sensor data streams. We compute a phase schedule that optimizes local flow, and then we send commands to the light, to the controller, to when it's time to change to the next phase. Schedules are also communicated to the downstream neighbors. That indicates what's coming. And then this whole process sort of operates in a rolling horizon fashion where we repeat the cycle every few seconds.
Do the sensors just see the first car there, or do they see further down?
They see farther down, essentially. We see the vehicle flows over some prediction horizon. So let's take a look at some of the components. First of all, let's look at the core intersection control. Let's see, The basic idea here is to treat online planning as a single machine scheduling problem. We exploit aggregate representation of traffic flows to identify the input jobs. This aggregation captures the non-uniform or retains the non-uniform nature of real-time flows, but it provides us with a much simpler search space, more efficient search space to move. The problem is still exponential, but it's exponential now in the number of jobs rather than in the planning horizon. And that turns out to make a big difference since the number of jobs is much smaller. The basic approach then is to construct a look-ahead schedule for current input flows and then use the result to decide whether to extend or switch phases. So here's the kind of representation of the flow representation that comes as input to the system. Over some planning horizon, you have an intersection on the left, cars are moving towards it, and the flow representation is essentially a sequence, a timed sequence of clusters, or jobs as we'll call them, that are moving. At the lowest level of time resolution, they could be individual vehicles, but depending on the time resolution, they may be aggregated into sets of vehicles. We actually, we perform two types of aggregations on top of this base flow. First, which we call threshold-based clustering. Really, the idea is just to merge clusters with small gaps into what you might think of as platoons of vehicles that are moving sort of in a crowd. So you can see that there. A second kind of cluster aggregation that we'll take advantage of is what we call an anticipated queue. One aggregate cluster is obviously the set of vehicles that are sitting in the queue waiting for the light to turn. The idea of the anticipated queue is really you just add to that those vehicles that are sitting in the queue and those that will arrive at the queue before the queue clears. So here's suppose we have two flows, input flows 1 and 2 here, green, one's got the green light, the other's got the red, and what we'll consider to be a schedule will be a sequence of all the clusters. So that'll be basically the basic scheduling problem, to sequence the clusters. Once I have a schedule, that implies one or more planned single sequences, depending on the exact timing of the sequence changes. So once I have a schedule, I can translate that into a planned sequence. So then the problem is going to be, the problem we'll solve is to minimize the cumulative delay of all jobs subject to basically timing constraints on safety and fairness. So safety is the yellow period and maybe the all red period when you're switching phases so that cars are safely separated. And fairness, there's typically a minimum and a maximum green time associated with every phase so that each vehicle will get some attention. The core scheduling strategy then, how we solve that problem, we use a forward dynamic programming search. A new job is added at each decision stage. Since we're minimizing cumulative delay, we can establish some fairly strong pruning conditions, and dominated solutions are eliminated at each stage. We also only keep the minimum delay solution for each extension. So this is a greedy heuristic, but it seems to work pretty well. And as I said before, the complexity now becomes a function of the number of jobs, given the aggregate representation that we're reasoning about. One just quick note that in related work, this procedure has been shown to outperform other state-of-the-art approaches to intersection control if we assume a road network is being driven with just intersection control and no further coordination. But we're interested here in adding coordination to the mix. And as I said before, the basic protocol is essentially to optimistically assume that all neighbors will follow their schedules and communicate planned output flows to downstream neighbors. So the idea here is very straightforward. We communicate, we build a schedule, communicate it to our downstream neighbors. They use that to extend their prediction horizon and can generate in an expanded planning horizon, can take in those predicted flows into account. Some properties of the basic coordination mechanism it's quite scalable, since communication is only restricted just to direct neighbors. But at the same time, you do have the ability with a sufficiently large planning horizon to incorporate the impacts of sort of non-local, multi-step, multi-intersection impacts. One final, but again, for that coordination to work, we assume that everything is operating perfectly, that we're executing schedules exactly as planned. There are two situations that where we need to cope with miscoordination. Since the intersection controller treats jobs as indivisible, it solves a problem as a preemptive or a non-preemptive scheduling problem. It is possible that a planned output flow can violate the maximum green times of a given phase. So to avoid that kind of miscoordination with downstream neighbors, the post-process is added where input clusters are split as necessary to allow enforcement of maximum green time. And then we just iterate with the intersection scheduler to get a conflict-free solution. Another, as I mentioned previously, the physical capacity of the road could also cause problem in very high congestion periods, a phenomenon called spillback. We recognize, in this case here, the downstream neighbor will recognize the spillback condition, basically a competing flow where the residue queue is going to exceed the physical capacity of the road. And in that case, we'll cut the current phase short, essentially sacrificing the flow that this intersection could get to better service the upstream intersection. So those two mechanisms then sort of layer on top to work that. So let's look at some experimental results to sort of evaluate essentially the idea was to evaluate the effectiveness of the coordination mechanisms over the base. So we designed a synthetic grid network to kind of provide a structured but yet challenging problem. Very small temporal resolution to allow us to actually do the real-time computation. Short intervening travel times and high congestion. So for this experiment, we have a 25 intersection grid. All roads are one way in this grid, so they're either flowing left or down. There are two major flows, the flow originating at C and the flow originating at 3, and they generate 3/5 of the overall traffic. So that's really the bottleneck flows, and all other routes have 1/20th of the flow. Simulations run for an hour. Essentially, shifting the demand ratios, the amount of traffic, relative amount of traffic on C and 3 every 20 minutes for a total simulated period of 100, and then computing the waiting time averaged over 100 runs. So here are some of the results. So what we compared is, first of all, the schedule-driven intersection control mechanism by itself, no coordination, along with this sort of versions of the system that incrementally add more of the coordination. We also compared to two other techniques, a technique called balanced phase utilization, which does coordination by computing cycle offsets and propagating offsets through the network. This is a technique that's used in many contemporary adaptive systems. And then a final technique where we combined the intersection scheduler with moving average prediction, which is another current approach to this kind of coordination problem, and see how that goes. So the results are discussed a good bit in the paper, but we can see that we kind of got the effect that we want, particularly as congestion gets, or as demand gets heavier, the value of the incremental value of each of those coordination mechanisms makes more and more difference. Interestingly, I guess, the competing techniques actually fare pretty badly here, particularly as the demand moves higher. I think I'm going to, there's a discussion in the paper also where we looked at varying the horizon extension of the thing. The bottom line is that for any horizon we tested, the largest horizons we tested, the computation times really never exceeded maybe 20% of a second, 0.2 seconds. So we really are solving this essentially order of magnitude faster than previous techniques. But I'll leave that to you, and I just go and spend a minute or two talking about a more recent activity. So for the last 6 months or so, we've been actually trying to do a pilot implementation of this strategy in an area of Pittsburgh. The area that we're working in is a developing area of Pittsburgh, and under sort of a recent construction project, grid of 8 lights intersections was upgraded, and they put cameras on them, and so it was a great opportunity to do it at a relatively low cost. We added a 9th intersection to make it more of a grid structure, and so we put computers at all the intersections. They talk to each other, and they're running. We are in the midst, I guess, of doing a pilot evaluation right now, where we essentially are doing identifying the 12 heaviest utilized routes through this complex of intersections, and we've done a series of drive-throughs before using the timing plans that are in force today, and then again after sort of while our system is running in place. The existing timing plans were developed at the time the intersections were put in, the new intersections were put in. It was really an optimization that was done offline based on expected flows. You can see that we haven't completed all the periods of the day, but for the 2 most significant periods of the day, the AM rush and the PM rush, we're actually doing very well in comparison to the previous technique. Travel times are being reduced by 25 to 30%, wait times 40 to almost 50%, and doing the derivative calculation for emissions, you can see that we get a reduction. Actually, our funding agency is really interested in reducing pollution, and that was really the original motivation for the pilot. So let me just say a few in conclusion here. I guess schedule-driven coordination can provide an effective practical basis for real-time control of traffic networks. The aggregation of traffic flows enables efficient computation of near optimal local schedules, exchange of schedules, then extends the local visibility to anticipate future demand. And also, you know, since this is an asynchronous, decentralized operation, it makes the approach inherently scalable. To add a new intersection, you just add a new intersection. And there's no, so we're actually in the pilot implementation, we now have plans to sort of double the implementation and really sort of demonstrate the scalability. Some of the, this last slide, some of the future directions we're going. One of the things that we are looking at currently that we'd like to incorporate is to extend the intersection scheduling to incorporate what's called phase skipping. The idea here, you know, I said we went in a fixed cycle, but a lot of times it's really advantageous if you're able to skip phases. You know, say a protected green left. If there's no cars sitting there, the rest of the intersection is dead while that's green. So it really, you can think of it, it makes it almost more of a planning problem because you can view phase selection now more as a selection problem than just a straight sequencing problem. We're also interested in better coordination mechanisms. As you can see from the talk, we do relatively simple things right now. The efficiency of the intersection scheduling, though, gives us a lot of headroom to do more sophisticated kinds of coordination. And it's clear that in some situations that makes a difference. And finally, we're very interested in taking a more principled look at tolerating sensor uncertainty. We've got a variety of mechanisms in our pilot implementation now to kind of cope with the fact when cars miss the data zones and we have mismatches in counts and so on. But with a complex of sensors, there should be better ways to compensate from one place to another. So I'll stop there. Thank you. Yeah. Oh.
Thanks, Steve. It was a great piece of work. First an observation and then a quick question. I visited traffic control centres in the UK, and I think we discussed this a little bit yesterday. They do use Scoot, and they basically the traffic managers tell me they just sit back and let Scoot do the job. It would be really great to see a comparison between Scoot, which is an adaptive system used around the world actually, and this. That would be really, really interesting. And the second, the question is, would this scale to a whole city centre?
Yeah, I think it would. I mean, we would like to get the opportunity to try that, but you know, since it's all local coordination, and it's, you know, there's some when you add light, there's some amount of tuning that you do, but you know, we're learning that there's a couple classes of nodes, if you want to think of it that way. There's always the nodes on the fringe that have less detection than the interior nodes. But other than that, those kind of broad classes of situations, it's, you know, that's I mean, systems like Scoot have more of a hierarchical structure to them and try to sort of manage them, you know, with more of a global view. And you know, that's a natural obstacle to scalability. It's a lot of complexity that we don't have to deal with, basically, to get bigger.
So the next talk will be by Sabine Storant on route planning for bicycles, exact constrained shortest paths made practical via construction on highway.
Thank you. So yeah, today I want to present my work about exact constrained shortest path. More exactly how we can speed up query answering, several magnitudes to answer queries like route planning for bicycles. This is just an example for a large range of applications you might think of in this scenario. So let me give you a bit of motivation. Why route planning for bicycles? Well, it's one of the examples where one objective is just not sufficient to describe the real goal. So for example, if you want to go from A to B by bicycle, you would like on one hand that the route is short, but on the other hand you would like also to avoid hard climbs. And if you just concentrate on one of the goals, you can see what happens in the map on the right. So the shortest path is given here in red, and the path with the minimal height difference is given in black. And the black path is about 3 times as long as the shortest path, while the shortest path has a significant high amount of meters to climb, so both are not really satisfying. So what we would really like to have is something like the shortest path, where we have a given limit on the meters we go uphill. And then we really want to have the optimum, right? So you can see the purple path in there is a really nice compromise. It was retrieved by setting a high difference bound to 1.5 times the minimal one. And we see it has significantly less climbs in it than the shortest path, but it's not that longer. So that's what we would like to have. And yeah, what's keeping us from getting it is that this is an instance of the constrained shortest path problem. And that's of course in pure Harding channel. So therefore we cannot really hope for polytime algorithms to solve this for us. And so we have to look what we can do to make still some effort in practice. Okay. Some notations. So what they're given is a graph, or more precisely in this scenario, a street graph. And every edge has 2 costs assigned to it. So the costs in the normal sense and also resource consumption. And we would like to solve this LP. So on period time, there's also revealed the start and the target vertex, and some bound on resource consumption, and we would like to minimize the sum cost and around some resource consumption cannot exceed this given limit. So for our specific application, the costs are the Euclidean distances in 2 or 3 dimensions, however you like, and the resource consumption is the positive high difference. That means that every downhill edge and every flat edge will receive the resource consumption of 0, while the upper edges have a resource consumption that equals the difference of the node elevations. So what I want to show you today is where we can adapt speed-up techniques that were originally developed for the conventional shortest path problem to also speed up our queries with resource consumption, and as a nice side effect, we will also be able to reduce the space consumption significantly. So the focus is really on solving the thing exactly in very large speed networks, and while in the paper there are more techniques, I will focus here on contraction hierarchies, which I will present in some seconds. So how can we solve the constrained shortest path problem normally? Well, there's a very wide range of things you can do. You can do LP relaxation and gap closing methods. You can do path enumeration. I will use the label setting algorithm as a basis because it has a nice property that is closely related to algorithms that we use for the conventional shortest path problem. So what a label setting algorithm does is it designs to each node the list of all the Pareto optimum tuples. And Pareto optimum means where optimum with respect to at least one of the metrics, so cost or resource consumption. That means there exists no dominating path. Dominating is just another word for better in both of the criteria. So here's a little example. We want to go from S to T. And the tuples represent cost and resource consumption in that order. And what we do is, well, first we assign to S, of course, 0, 0, as we have not used any cost or resource consumption at the start. We use a priority queue that sorts these kind of labels by the costs. And now we perform edge relaxation. That means we extract the first node from the priority queue, look at all outgoing edges, sum up the labels, and attach new. So in the first step, nothing really special happens. as well as in a second, but now we have a look at node D. You relax the edges, 1 towards C. C will receive a label with a cost of 5 and a resource consumption of 6, and which will be a dominating solution for 511. So we will replace the solution, like you can see here. And now we want to relax the edges from C. And we see B will now get a second Pareto optimal solution assigned to it because the new one has less cost by the higher resource consumption. So as T gets a second label. And if you go on, we see until the priority queue runs empty, T will receive 3 Pareto optimal solutions, and it depends on the given resource bound which of them we will declare optimal. So for example, if the resource bound is 12, we will select a solution in the middle. If it's 7, we will have to select the path which has a length of 13. Okay? So this is how the labels algorithm works. And we see it's very similar to Dijkstra's algorithm. So it operates directly on the graph, it uses a priority queue and edge relaxation. There's also a bidirectional inversion. But the difference, of course, is Dijkstra's algorithm runs in polynomial time. There's always only one label assigned to each node. While here we have, as much as there are paths between the source and the vertex, so there can be an exponential number of labels for each node, and we have to store them, which costs, of course, a lot of space, and we have to relax all of the labels, and which was a lot of time. So people already thought about how we can prune the search space effectively, so that we do not have to look at this many nodes and edges. And a nice and simple idea was presented by the same people who implemented this algorithm. And the idea is first to only consider the resource consumption, so we forget about the cost for a moment, and what we do is we build a lower bound on resource consumption, which can be easily retrieved by 2 Dijkstra runs only on resource consumption from S and T. And then we see something like that, so for example, the node in the middle, it needs at least a resource consumption of 10 to be on any path from S to T. So if you're given a resource bound of 7, we know this node will not be on an optimal path. We can prune it right before. Okay, so it's a very nice technique, and this has a great impact in a lot of applications. But what we also see, if we increase the resource bound, more and more nodes become feasible again. And so the impact of this technique is low. On the one hand, if R is very large, but on the other hand, also if there are a lot of edges with a very small resource consumption. And unfortunately, that's exactly the case in our application, because remember, all the downhill edges and all the flat edges will receive a 0 resource consumption. And so this technique was expected, and also our experimental results revealed that the impact is pretty low. So we get a speed up of maybe factor 2 or 3, but that's all we can get. So that's just not enough to answer queries in very large graphs in practice. So we thought about a pruning technique that might be more robust against distribution of resource consumption. And we came up with a version of contraction hierarchy, which is a very nice graph preprocessing method developed by Gasberg et al. In 2008. And yeah, it's very widespread because it's nicely transferable to a lot of sophisticated applications. The basic idea is to add additional edges to the graph that allow us to skip a lot of other edges on queue time. And it works as follows. We first assign distinct importance values to all of the nodes. Do not care the moment how we do this. This is some heuristic work. Okay, and then we remove the nodes one by one in the order of importance, while maintaining all the distances between the remaining nodes. So, for example, if you want to contract the node in the middle here, the black one, we see that between the node with importance 37 and 64, the shortest path will no longer be 3, but will now be 6 if we remove this node. So in order to maintain the distances, we have to add an additional edge with cost 3 between those 2 nodes, like you can see here. Between, for example, the node labeled with 37 and the node with 12, the shortest path is 3 and will stay free if we remove the node in the middle, so there's no shortcut needed, and we call such a shorter path a witness path. So very essential to kind of keep the number of edges we have to insert small. So if you've done all of that, so all the nodes are away, we just add all the shortcuts we created during this contraction process, add them to the original graph. And what now happens, very interesting, every shortest path in this new graph, original plus shortcut edges, can be divided in a path that goes first only upwards. Upwards means only to nodes with high importance, and then only downwards until it reaches T, so to nodes with low importance only. And which really decreases the search space significantly, because now we can perform query answering in a bidirectional manner, so we just relax edges to nodes with higher importance in this bidirectional version. So like you can see here, between any of these nodes, there's a path that only goes upwards first and then only downwards. Okay, so that's the crucial part. So now how can we adapt this for our scenario? What we have to do is we have to find a new way of contracting the nodes and maintaining all the optimal paths. And now we do not only have to maintain all shortest paths, but all Pareto optimal paths. Because if the long Pareto optimal path is piecewise Pareto optimal, so if we maintain anything on the local level, we can be sure to guarantee optimal query answering in the end. So how can we find a witness? Well, the witness is not only shorter now, but it must dominate the reference path. So we can only omit adding a shortcut if there's a dominating path. Like you can see in this small example, if we look at the node in the middle, the red one, we'd like to contract it. So a reference path will be the one from U to W over V. It has cost of 10 and a resource consumption of 7. And now we look at the blue path, it has less costs, but a higher resource consumption, so this is not a witness. But the green one we see below, it has costs of 5 and a resource consumption of 3. It clearly dominates the reference path, so we know in this case we would not have to insert a shortcut. So, question is of course, how can we find such a dominating path? Well, you will say easy, of course. We know how the label setting computation works, so why not just start the label setting computation in U, let it run until we found a dominating path. If that is the case, we can omit a shortcut. If the PQ runs empty before that, okay, we know we have to insert a shortcut. Well, theoretically this would work, but the problem again is that the label setting computation is very time and space consuming. And while you can say, of course, this is a pre-processing step, I can take a week or so, but this really is the difference between you can really not do it if you do it this way. Unless you have a server farm or you work with Google or something like that. So how can we make this visible for normal hardware? And the idea is that we want to restrict this first to paths on the lower convex hull. Well, what's the lower convex hull? We can represent each tuple as a linear combination of the cost and resource consumption. And we say a path is on the lower convex hull if it's minimal for some lambda value between 0 and 1. So for example, you see lambda being between 0 and let's say 0.5. The yellow path is minimal in this example. When it changes over to the green one and then to the black one. So these three paths are the lower convex hull in this example. And the property of these paths is they are all Pareto optimal. While for paths that are not on the lower convex hull, we cannot say anything. So for example, the blue path is dominated by the yellow one. But the brown path, which is also not on the lower convex hull, it's not dominated by any other thing. So it's also Pareto optimal. Okay? So what's the advantage of paths on the lower convex hull? Well, they have the nice property that they can be found by a Dijkstra algorithm. We just have to transform the costs to single edge weights, exactly this linear combination, and then we have Dijkstra's algorithm, which runs in polytime, which has a limited space consumption, so which is something we can do very fast. So, questions are, of course, in which cases does this help us, and what can we do if this does not? So, well, if the dominating path is part of the lower convex hull, we just found a witness, and we know we can omit the shortcut. So remember our example here, we see now the representation of the lower convex hull. We see the green path is the complete lower convex hull, so any Dijkstra run of any lambda value will give us the witness path right. Okay, but that's not all. The other way is that the reference path is part of the lower convex hull. If we find a reference path by trying some lambda value, we know the reference path is Pareto optimal, therefore it cannot be proved. We know we have to insert a shortcut. Okay? So, yeah, but this procedure might be inconclusive. We cannot guarantee that one of these cases will always apply. So it might be that neither P nor the possible witness path are part of this lower convex hull. And on the other side, you will not be able to test for every lambda value. There might be just the number of support points you select, and which number might be too small. So in the paper there's some ideas, some heuristic, how you can maximize the output for a certain number of lambda values, but still it might be not enough to get a conclusive result. And what we can do then is, we can of course apply length computation on top, but we could also add a shortcut. So shortcut insertion, even if the path is not Pareto optimal, does not compromise optimality, but of course it will increase the search space and the space consumption during query answering, so it should be avoided as much as possible. So let's come to some experimental results. We used test graphs ranging from 10,000 to 5.5 million nodes. They are all cutouts from the graph of southern Germany, because this is at least a bit of mountains there. So if we could also do this on whole Germany, but then the optimal paths differ not too much because it's pretty flat in the northern part. Okay, and we used 3 support points, so 3 different lambda values for our check procedure, so to search either for a dominating path or a witness path on the lower convex hull, and we get a conclusive result in over 62% of the cases. That means in all of these cases you could save the label-saving computation, just use Dexter's algorithm to get a conclusive result. And kind of surprisingly, the number of edges in the resulting structure, so in this graph, original graph plus shortcut edges, was only about twice the size of the original graph. This is comparable to the conventional case, if you just compute the whole thing for conventional shortest path, which is kind of surprising. We kind of expected a larger increase in the number of edges, because you have all these Pareto optimal paths that you have to maintain, so there might be now several edges between 2 nodes, but still it was kind of benign in our application. And what we get as a result is a query answering that is sped up by about 2 orders of magnitude. And this is only the unidirectional version of the problem, so which was reported in the paper because you can compare it to other search algorithms that are not bidirectional. But if you implement it in a bidirectional manner, you can even get another order of magnitude. So we have a speed up of thousands, in fact. And also we have a remarkably less space consumption, because we have to take a look at much fewer Pareto optimal solutions, and just using simple pruning, some of the queries in this 5.5 million node graph fail even on a very large server structure, because there are thousands of Pareto optimal solutions assigned to each node. But yeah, applying our technique, this thing here could solve all of it. Okay, so conclusions. Well, we can answer exact constraint shortest path problem in graphs with up to 500,000 nodes below a second. In a graph with 1 million nodes, we need about 2 seconds, and then it decreases a bit, but still it's really practical query times now. And if you're interested in the paper, there's also a version how we can speed up dynamic programming solutions, and how we can use argflex for further speed up. Argflex are another technique originally developed for the shortest path problem that helps to prune a lot of edges. And yeah, future work. Well, what contractual hierarchy does is it gives you the opportunity to extract a very small subgraph in which you can guarantee optimal query answering. So if you have any other speedup technique in mind for that problem, you can apply it on a smaller graph. You can apply it on top, and there might be even greater speedup than that. And also it would be interesting to see other metric combinations and maybe more complicated scenarios. So for example, the edge clustering functions. So contractual hierarchy works very well in every case. There is some hierarchy on the graph, so there are more important edges than others. And so, for example, if you would use travel time instead of distance, we would expect an even greater speedup. But for many other metrics, we just don't know. It would be interesting to see how it performs in these cases. So, thank you very much for your attention, and looking questions.
How your algorithm is actually...
Thank you. So, how this work is actually different from the Google map and it proposes the bicycle route?
Oh, the Google map thing doesn't use constraint shortest paths. It just gives you the shortest, and it does not even that. I think it gives you an approximation of the shortest. So there's no constraints in it at all.
There are some constraints like that. it should not be like very busy route. I mean, let's say it should not go to the main street of the
Yeah, that's true. So you can, of course, prune edges that you're not allowed to use, but that's not constrained shortest path. I mean, it's just taking a subgraph and answering queries in this subgraph and not constraints on this. So you're really not allowed to use them, not you can use a special amount of that. So it's a difference.
Okay. I mean,
Thank you.
Okay. So in your resource function, you had only positive and zero costs.
True.
What if you would have also negative costs from, for instance, recuperation of energy in an electric vehicle? Is it
Yes.
also feasible?
Yeah. So if there were to occur negative cycles, of course it will not be possible anymore because there will be nothing like an optimal path in that scenario. But so there could be negative costs in both, also in cost or resource consumption, and we could apply a transformation of the graph that just gets rid of these negative edge costs, and we could still guarantee optimal query answering. But yeah, you have to make sure that there are no negative cycles, otherwise everything will crash.
how do we determine? Maybe I think I missed that part. How do we determine that where are hard climbs in the path? Let's say there is a roadmap, and then how do we determine that where are hard climbs and where are splits?
Yeah, I mean I have the node elevation of all the nodes, and I mean edges are specified by head and tail node, and so I know it goes uphill if the elevation of the tail node is larger than one of the head node. So I mean, it might be a bit simplified because in reality there might be paths between two nodes in OpenStreetMaps that are a bit longer and not just straight line, and they might not be that exact, but I think the data is sufficient to suggest a very nice route.
So a map will give you all those numbers, right?
Yeah, so the node elevation you got from SRTM, so it's really precise. You can, if you extract the raw data, not the already, yeah. Yes.
With 500 Ks of nodes, you had a response time below 1
Second.
yeah.
Yes.
And how did this scale up?
Yeah, of course so the one thing is, so I said about 1 million, we took about 2 seconds, so this was really benign. In the paper, for the larger graph with over 5 million nodes, we made an incomplete contraction to make the preprocessing time smaller. If you really let it run for the end, it has some seconds, but it's, so for the incomplete contraction it's about a minute for this very large graph, but if you let it run to the end, it's some seconds, and if you use the bidirectional version, you can get real time.